Hello, we're back again. Today's topic is going to be acid rain. We're going to discuss a little bit about what causes acid rain and what are the effects of acid rain. This will fit somewhere in either Tuesday, April 14th, probably is where this video is going to end up being housed. So let's get started here. So acid rain or acid formation, acid precipitation, it goes by a lot of different terms, is any rainfall that has a pH of less than 5.6. Now, if you remember, anything under 7 is considered an acid. So there's really a few major ways this occurs. One way for acid deposition is through sulfur dioxide and nitrous oxides that get into the atmosphere combined with water to form sulfuric and sulfurous and nitrous acid that comes down as rainfall. These are generated from the combustion of fossil fuels, from trucks and automobiles and factories and things such as that. Once these sulfur dioxide and nitrous oxides go into the sky, they are going to come out as acid rain. That will have biological effects. It will reduce crop production. Most food products like to grow in a slightly basic soil. That would be above 8. So clearly a pH of 5.6 would not be good for food production. It also can be corrosive to marble and different metals. It's corrosive too. Acid rain in general is just not a good thing. So what we want to do is kind of look at the U.S. and see if we can see any kind of pattern. So let's look first at sulfur dioxide gas and see how that affects. So we're looking at sulfate ion concentrations from 1984 through the years 2003. And what you notice is the Rust Belt, this area on the East Coast, we're thinking about steel production and so on. There's going to be quite a bit of acid rain there. Now, by the time you get to 1990s, late 1990s, 2000, a lot of the manufacturing in the U.S. has gone away, and that's really improved the sulfate ion concentration or diminished the amount of acid rain across the country. Besides losing manufacturing, a lot of the industries that would have polluted now use what are called scrubbers to clean the sulfur dioxide gas that would be going up the smokestacks. We'll describe scrubbers here in a little bit. But overall, it's looking much better across the country from that. Let's see, somehow we want to go back. Let's look now at the nitrous oxides, okay? And when we look at these, we're looking at the same period of time, and we can see those concentrations again. They're diminishing. I'm not really sure what's happening over here, why we got such a big load there. Now, you might anticipate California would have much higher concentrations, but California actually is very good at limiting the amount of pollutants in their gasoline. They do pay a premium price for their gasoline to make this happen. But again, that's a choice people have to make. It's densely populated, but not a huge amount of acid rain occurring there. Okay, you can see up here you've got Michigan still has a lot of automobile manufacturing there, a lot of industry that still pollutes, and that's what's causing the problem there. All right, let's keep on moving here. So let's talk about how this acid rain might occur. So we have here, we have an S, that's the yellow, O2, the two reds, so sulfur dioxide molecule colliding with, this is water, H2O, and when they get together, it makes sulfurous acid. So here's the reaction that's occurring in the atmosphere. Sulfur dioxide gas plus water liquid turns into sulfurous acid. Now, what can also happen is two sulfur dioxide molecules and an oxygen can collide and make two of these SO3 molecules. And then the SO3 can be collide with a water, and then this will make sulfuric acid. So you can see how sulfur dioxide can make both sulfurous and sulfuric acid. And both of these, again, are major components of acid rain. And the last example, we're looking at sulfur dioxide and hydrogen peroxide to form sulfuric acid. That's probably a little bit less common, but another way that acid rain could be formed. On this chart, this is from the National Atmospheric Deposition Program, and we're looking at, and I apologize, the data is a little bit old, from 1999, but you're looking at the pH of water that you're getting in the different areas. And you can see a lot of the water's around pH 5.5, 6 range. And then you get over here toward the Rust Belt, our water's in the range of 4.5. Now the difference of 4.5 to something like 6.5, that's 100 times more acid in this Midwest region where we live. So that's something we definitely need to be concerned about, where that's coming from. Where is that acid coming from? Because we know it's not good for farming. This one's a little bit harder to see. It's basically the same type of data from 2003. Not seeing any big changes in trends there. We're still seeing areas that have the lowest pH levels in this region of the country. Again, a lot of this is due to manufacturing and the combustion of fossil fuels. Another contributing factor would be that this area of the country is far less populated, and so there's fewer automobiles and so on. Now, even though California is relatively densely populated, remember their cars have to pollute less. That's one of the things they have to do, is buy cars, get them tested for smog and so on, and that it makes a difference. We mentioned earlier about these smokestacks that pollute sulfur dioxide. You can see all that pollutant going up the smokestacks. And that, when it combines that sulfur dioxide gas with water, is what gives us a lot of the acid rain. Now we're looking at sulfate ion in 2006. Now, if you've been paying attention, the level from 1999 to 2006, these levels have gotten less and less and less. So we are making progress on acid rain. Here's a marble sculpture. I think it was photographed outside of maybe Chicago. I'm not sure. And it's sad that it's starting to corrode from acid rain. But again, this is an early warning sign of the dangers of acid rain, and that potentially could have some problems to us. I'm not sure what they might be, but in any case, I would be concerned when I see stone crumbling from being exposed to the air. I wonder what it does to our bodies as well. All right, let's now talk about that coal burning power plant. So this graphic might look familiar to you if you remember from the nuclear power plant. All power works by turning a turbine to make the energy. Well, in this case, we're going to pump coal in. We're going to take trainfuls of coal and we're going to simply burn them in the boiler. Then we're going to have a water line that goes through, and that water is going to come here, and it's going through a series of pipes where it's going to be heated to the boiling point. And as it boils, it turns to steam. Then that water will turn the turbine because it's hot. And then additional water will go over it to cool it. And that's what we're seeing here. The cool water comes in and cools off this water, and some of it is heated up. So there's a closed loop here. Now the problem is right here in the smokestack, this little dark gray stuff is actually could be far, far worse. So we're billowing out carbon dioxide, we're billowing out sulfur dioxide, nitrous oxide, and carbon particulate, none of which are particularly good for the environment. So they do a chemical reaction inside the smokestack to control some of those gases. So here we're looking at what the chemistry of that would be. So here we have the boiler where you're burning the coal. The water is going to be heated in these tubes that go sideways, and then the gases that come out here, you can see what is going on. We've got shelves that have in here some calcium oxide and water. So the flue gas that has sulfur dioxide is going to be blown into the scrubber, and as that combines with the calcium oxide, you've got calcium oxide and water forming calcium hydroxide. then you've got sulfur dioxide and water making sulfurous acid. Well, here's how we get rid of that. The sulfurous acid, that's an acid, is going to be neutralized by this base, calcium hydroxide, formed from our calcium oxide, or our quicklime. And that's going to produce an insoluble hydrate, calcium sulfate dihydrate. And then this stuff, of course, will form as a solid and can be gotten rid of. And so the net result is, instead of having sulfur dioxide gas go into the atmosphere to make sulfurous acid, it's going to be sequestered or gathered as a solid, and then the smokestack will be only putting out water vapor or much less pollution than it was before. That's what a chemical scrubber is, or a scrubber, if you've heard about that, for a smokestack. Let's look at maybe how acid rain might form. Here's another version of acid rain that we hear about all the time. We talk about carbon dioxide. So carbon dioxide is gas at room temperature, and water is a liquid at room temperature. And the water and the carbon dioxide can actually combine chemically to form carbonic acid. It is a weak acid. So let's talk about and see that here. So here we have the carbon dioxide and the water, and they sort of get together. Notice how once they get together, they're going to have a conformational change. And we just saw the water donate a proton to the carbon dioxide. And now what you're left with over here is the carbonic acid. You have H2CO3 carbonic acid being formed. So we can look at that one more time. Here's your carbon dioxide and your water getting together. There's going to be a transfer of the hydrogen, and now we end up with our carbonic acid. Carbonic acid, again, is a weak acid. That doesn't necessarily mean it's extra safe because it's weaker. It simply means it doesn't dissociate fully in solution, and we'll have to discuss that on a different level.